Right now, to get this webinar started, I'd like to introduce the marketing manager at Dynapower Company, LLC, Richard Morin. Richard, go right ahead.
Thank you for joining us today for a webinar on comparison of IGBT chopper and Thyristor Rectifier technology, brought to you by IEEE and Dynapower. But first, a bit about the Dynapower Company. Founded in 1963, Dynapower is a global leader in the design and manufacture of high-quality industrial power conversion solutions from high-power SCR, IGBT chopper and Thyristor rectifiers, and custom transformers to energy storage inverters, DC converters, and fully integrated energy storage systems, as well as military-grade power electronics. Each is designed and manufactured in Dynapower's 150,000 square foot manufacturing and engineering facility in South Burlington, Vermont. Dynapower designs, manufactures, and tests integrated high-power transformer rectifier systems for use in many heavy industrial processes such as electrowinning, electrochemical, electrorefining, electroplating, anodizing, and other specialized applications worldwide. Dynapower designs and manufactures the complete rectifier control systems for use in our high-power rectifier systems, including the main semiconductor controller, gate drivers, and base conversion process control. A full control, metering, monitoring, and fast production scheme is integral to all Dynapower rectifiers, as is a fully integrated operator interface and control system for a single unit, or an entire multi-unit supervisory control and data acquisition network. The company's high-power rectifiers are engineered, designed, and manufactured and tested to internationally recognized standards including ANSI, NEC, IEEE, IEC, NEMA, UL, CSA, and JEC. Dynapower has over 55,000 pieces of power electronics in the field worldwide, serving an array of clients including the U.S. military, Los Alamos Labs, Apple, Tesla, NextEra, Freeport-McMoRan, Dow Chemical, Olin, Chemtrade, Occidental Chemical, U.S. Steel, Ford, and Boeing, as well as an array of smaller plating, anodizing, and other types of metal finishing businesses and research and test labs worldwide. Today's presentation will concentrate on the fundamental differences between Thyristor and IGBT chopper rectifiers. Dynapower manufactures both chopper and Thyristor-based high-power rectifiers for large industrial applications worldwide and has successfully been doing so since 1963. There are several key technical considerations for evaluating high-power rectifier topologies that engineers must consider before recommending the optimum rectifier configuration for any project. These include power factor, harmonics, transformer design, ripple, efficiency, as well as space and installation requirements. In particular, today we will describe the advantages of IGBT chopper rectifiers, which employ diode rectification in the front in a modular configuration, versus conventional Thyristor-based rectifiers. Controls. The major difference between the two topologies lies in the nature of power electronics devices used in the power converter. Therefore, the electronic boards used for the circuit control will be different. Thyristor devices are phase sensitive with a gating pattern that has to be synchronized and dependent on zero crossing. The response time of phase controlled is dependent on turn-off time of the Thyristor and typically is between 50 and 100 milliseconds. Once turned on, the reverse current of the AC line must commute it off, increasing the response time and putting stress on components. Thyristor control is sensitive to the presence of noise on sensing and gate control signal wires, and misfiring of the devices can occur, causing damage to the system. On the other hand, IGBTs in the chopper topology are not phase dependent and do not require synchronization. Diode bridge on the front provides initial DC rectification without phase sensitivity. Transistor control is high-frequency PWM with fast response time, as the semiconductors do not need special turnoff. The response time is around 100 microseconds, 1,000 times faster than the Thyristors. The electronic boards used to control both topologies are developed, controlled, and maintained and guaranteed by Dynapower. That gives us flexibility, confidence to supply and maintain our product and guarantee the life of spare parts for both chopper and high-power Thyristor rectifiers. Thyristor rectifiers. The Thyristor is a semiconductor device which can be used to switch current on and off. When used in rectifier circuits, Thyristors allow current to be controlled accurately, letting current pass in a graduated manner by firing at a precise time, therefore controlling the conduction angle. In a thyristor arrangement, phase-controlled PFC modulates the thyristor into and out of conduction at a predetermined phase of the applied waveform. In general, the main advantages of thyristor rectifiers are high efficiency, high reliability, good control of the load current, and is a mature technology that has been applied for many decades. The disadvantages are generation of reactive power, generation of current harmonics, special transformer design, and the need for harmonic filters. Chopper rectifiers. Chopper rectifiers use a combination of diode rectifiers and power transistors to generate large controlled current. The chopper rectifier design consists of high-frequency switching technology in a modular package that converts AC voltage to a regulated output DC voltage. Large power systems are constructed of multiple chopper modules to obtain the specified current requirements. Each section of modules has a separate set of sensing and protection and is controlled by the main chopper control. The operating advantages that we will examine today are power factor, harmonics, ripple, transformer design, system response, efficiency, and system size and cost. We will examine each one at a time. Power factor. A high power factor results in voltage and current being closely in phase with each other. Phase-controlled supplies with retarded firing of the thyristors have inherently lower power factor. Typical thyristor rectifiers run at power factors in the range of 0.85. Primary tap changers, PF correction capacitors, or a regulating autotransformer may be used to improve the line power factor of thyristor rectifiers. Tap changers enable voltage regulation or phase shifting by varying the transformer ratio under load without interruption. But tap changers may have many steps and have a limited number of operations before requiring maintenance. In a chopper supply, however, diode rectification has no retarded firing and has constant high line power factor over a full operating range without the use of PF compensation. Typical chopper system power factors run at 0.925 to 0.95, with transformer K factors of 2 to 3, resulting in lower transformer losses. Typical thyristor rectifiers run at power factors in the range of 0.85 and K factors of 12 to 20, thereby increasing the line and transformer losses. Harmonics. Harmonics are distortions to the voltage and current running through a system due to nonlinear loads and components. Harmonics can have adverse effects, such as equipment heating and lowered efficiency, increased design requirements for rectifier transformers, and a need for compensating equipment. Harmonic voltages and currents are integer multipliers of the fundamental frequency. For instance, on a 60 Hz supplies, the 5th harmonic is 300 Hz, the 7th harmonic is 420 Hz, and so forth. In a thyristor-based rectifier, high harmonics are generated by the phase-controlled firing of the thyristors. Since the line current for thyristor-based supplies is typically rich in low-frequency harmonics to meet harmonic control standards, some way of harmonic compensation techniques, passive or active, have to be employed. As the input AC line conditions change, the tuning of line harmonic traps changes as well. This practice requires the application of a harmonic study in the early phases of the project. The chopper system provides a regulated DC output under large line variations, while maintaining low harmonics, allowing for the elimination of harmonic line filters in unit design and providing the ability to meet the harmonic limits of IEEE 519, the standard for recommended practice and requirements for harmonic control in electronic power systems, without these filters. As shown in the two diagrams, the input harmonics of the thyristor rectifiers are the function of the system configuration and the reactance of the system. The distortion of the line current waveform increases as the thyristor unit output voltage is reduced, while current amplitude remains the same as the output current. However, the chopper input line current waveform remains the same shape, but reduces in amplitude proportional to the DC output voltage. Transformer design. Kilovolt amperes, or kVA rating of the transformer, is the parameter used to size the transformer, showing how much current can flow through a transformer at rated voltage without exceeding a temperature rise associated with the rating. With a thyristor-based solution transformer, kVA is based on worst-case current and voltage for constant kVA, regardless of output power required. K-factors are specified higher for thyristor rectifiers. The higher the K-factor, the greater the harmonic heating effects. When a nonlinear load is applied from a transformer, it is sometimes necessary to derate the transformer capacity to avoid overheating and subsequent installation failure. Parallel combinations of 2 or more rectifiers in a system increases current carrying capability. For example, to gain higher current capability with reduction of harmonics in 12-pulse rectifiers, 2 6-pulse rectifiers could be connected in parallel. However, with a thyristor-based configuration, there is a need for an interphase transformer to absorb difference between DC voltages of the individual systems. Choppers require a lower kVA for the same output power, so transformer sizing is mostly based on output power requirements. Transition can be made from a high voltage line down to the required AC input for the chopper with a single transformer, in which each chopper section provides independent current control of each secondary. Chopper supplies can also tolerate unbalance between 2 secondaries while maintaining optimum harmonic cancellation without the use of IPTs, so K-factors are lowered due to reduced current harmonics. Chopper technology is a modular approach to rectification with a unit containing several chopper modules. The output of each chopper module is electronically regulated. This modular approach, combined with a higher power factor and lower harmonics, simplifies transformer design by eliminating the need for interphase transformers between the outputs of each parallel chopper system module. As an aside, Dynapower designs and manufactures complete transformer systems in-house, oil-filled, cast coil, and dry crate transformers. The transformers are manufactured using copper conductors and grain-oriented silicon core steel. All transformers are designed, manufactured, and tested in accordance with ANSI and IEEE standards, but other standards can also be considered as required by individual customers. Dynapower also designs and manufactures all water-cooled IGBT power chopper modules used in our chopper power systems. Further, a full control metering, monitoring, and fast protection scheme is integral to all Dynapower chopper rectifier designed and manufactured in-house at Dynapower's manufacturing facility in Vermont. Ripple. Ripple is the variation of the DC output within a power supply which has been derived from an alternating current AC source. It is the variation of the output alternating above and below the desired output due to the leftover AC from converting from AC to DC. Ripple can cause varying issues for output-sensitive processes. When the output voltage decreases from rated value in thyristor rectifiers, the AC ripple content increases. The output ripple for a 6-pulse operating system is 360 Hz, 720 Hz for a 12-pulse, and 1440 Hz for a 24-pulse system. At the same time, chopper rectifiers' ripple content is constant and not dependent of the circuit type. Therefore, the output voltage variation does not increase the ripple content. Chopper rectifiers include IGBTs with high switching frequencies resulting in lower output ripple, higher frequency output ripple, constant ripple over the operating range, less than 1 to 2%, elimination of the need for ripple filters. Efficiency. Compared at maximum rated output, the 2 types of rectifying equipment, thyristor and chopper power supplies, generate similar losses. However, the difference between the 2 topologies is significant at lower output power requirements. The chopper transformer losses are lower than the thyristor transformer losses due to the simplicity of the design and the significant absence of the harmonic currents. The transformer primary currents are similar in both chopper and the thyristor power supplies at maximum power factor and full output power. As soon as the thyristors are phased back because the line voltage is higher or the output demand is set lower, the transformer primary losses are higher due to the poor power factor and increased harmonic content. Additional losses in thyristor rectifier system are generated at harmonic filtering equipment, which is not the case for chopper rectifiers, which do not require. High efficiency means we are not paying for easily preventable system losses or to compensate for the unwanted power effects like harmonics, thus the advantage of the use of chopper rectifiers. Operation and maintenance. When conventional rectifier systems are employed, individual transformers are required for each controlled current output. whereas multiple chopper supplies or loads can be connected to a single transformer. Compared to their standard Thyristor Rectifier counterparts, chopper rectifiers also offer space and cost savings, with a high power factor, lower harmonics, simplified transformer design, and lower ripple. Chopper rectifiers eliminate the need for several systems and components seen in a typical Thyristor rectifier. Line power factor and harmonic line filters and ripple filters are not needed to meet line PF and harmonic limits, and this saves significant system space. Chopper rectifiers are sized to operate with N1 chopper module for greater reliability and quick module exchange. Fuse isolation enables the rest of the system operation in case of one module failure. System size and cost. Compared to equivalent Thyristor rectifiers and harmonic compensation equipment, chopper systems require overall less installation space. A major part of the cost of the system comes from magnetic components, especially the transformer. With the reduction of additional equipment and modular designs, the installation of the equipment is simplified. Chopper-based systems are easier to install and are up and running faster than their Thyristor counterparts. The initial purchase cost of the chopper rectifier system is typically less than Thyristor rectifier systems with harmonic filter and power factor correction system combined for equivalent operation. Long term, with higher efficiency, lower losses, lower input power consumption, higher power factor, and easier maintenance, chopper rectifier systems are economically much better and more efficient than their Thyristor counterparts as well. Let's compare the installation requirements for a Thyristor and chopper rectifier. For a Thyristor rectifier, there is the requirement for an installation of a larger kVA transformer, the addition of tap changers, the installation of the rectifier, installation of TNR switchgear, installation of HF-PFC network, installation of HF-PFC switchgear, additional switchyard area and security, installation of a deionizing system, installation of a larger system kVA capacity, installation of interface transformers. Whereas for a chopper supply, there is simply the installation of the transformer AN-SI31, the installation of TNR switchgear, the installation of chopper rectifier, the installation of T-chopper switchgear, and the installation of a deionizing system. In conclusion, chopper rectifiers offer several operational benefits over conventional Thyristor rectification. These include high line power factor over the entire power range without power factor correction capacitors. Diode rectification offers minimal harmonic distortion without the use of harmonic filters. Simplified transformer design eliminates needs for saturatable reactors and interface transformers, as current sharing and regulation is achieved by means of electronic chopper control. Elimination of space requirements for the line power factor and harmonic line filters leads to reduction in overall system size and cost as well. Chopper rectifiers are a modular approach to rectification. It makes maintenance easy if a module were to fail. Simply replace the module and get the unit up and running again in no time. In conclusion, simplified transformer designs paired with the elimination of power factor correction equipment, harmonic filters, and ripple filters make chopper rectifiers unbeatable for many applications. Prior to taking questions, we wanted to spend a moment on digital control upgrades for high-power rectifiers. The high-power rectifiers built by Westinghouse, GE, Satcom, InverPower, ABB, Siemens, and others more than 20 to 30 years ago are still in service and functioning throughout the world. In many instances, that equipment is on its last electronic boards available, therefore in an urgent need of new life and available spares and support. The cost to replace that equipment is an order of several millions of dollars in value, as well as months of lost production. Upgrading an existing aging high-power rectifier system with the latest digital controls is a cost-effective alternative to full system replacement or costly maintenance. A Dynapower control upgrades can significantly extend the operating life of an existing high-power rectifier system and provide improved performance, safety, and reliability. High-power rectifier control platforms are designed with specialized electronics due to rapid technology advances can quickly become obsolete, whereas rectifier transformers can last decades. Digital control upgrades can be an attractive alternative to rectifier replacement to improve the efficiency of many operations. When it is deemed safe to do so by our team of engineers, Dynapowers will recommend a control upgrade at the fraction of the cost of a new rectifier. Dynapower offers custom engineering and field service to modernize not only Dynapower and rapid power technologies, high power rectifiers, but all other manufacturers' rectifier products. We can supply a list of references of the equipment we've already upgraded throughout the world. A Dynapower control upgrade can be completed with minimal downtime and provide you with years of lasting service. Medina Merrick, engineering lead of the Dynapower High Power Systems Group, and her team will now take questions. Thank you to IEEE for hosting today's webinar, and we look forward to your questions.
Okay, thank you for viewing our Dynapower presentation today. Now, as a reminder, if you'd like to ask a question, simply enter into the lower section of the Q&A window and click Submit. Now, Medina, our first question asks, what is the criteria for selection of the best option for the application between diode rectifier, SCR rectifier, and chopper rectifier?
I just want to briefly thank everybody for participating in this webinar. This is the first of series of webinars that Dynapower will be launching through IEEE or through some other media. The question here with me are other engineers from Dynapower team that are here to help answer the questions and also learn from the participants what are the interests out there on the market and what do we need to do to improve our products and serve our customers better. To introduce them, here is a founder and a CEO of Dynapower, Mr. Peter Pollack, engineer himself that has been, along with his father, founded the company way back in 1963. Jay Motia is our chief engineer for industrial product line. He's also electrical engineer. Jay has been with the company for over 30 years. Mike Allen is electrical design engineer that has been working on chopper power supplies as well as on Thyristor power supplies ever since he joined Dynapower in 2004. So I will go back to questions. And the question was related to specific selection criteria for the best application between diode rectifier, Thyristor rectifier, or chopper rectifier. There are two basic lines and two basic processes that will determine which power supply and which topology would be the best for the application. There is the process side of design and design parameters from the process specific to customer, and the other would be electrical system factors. From the process side design parameters, we are looking at DC voltage and current for operating range that is required for the process, current ripple, current regulation accuracy, current regulation speed, DC voltage, DC power availability, and a redundancy concept for the customer, required overload capabilities. We will also look at the overall installation, whether we are supplying equipment that will be replacing existing equipment. We will look at the operational parameters of our equipment within customer's network as well. From electrical system factors, we will look at system efficiency, system reliability, repairability and diagnostics capabilities, long-term engineering service and spare parts support, investment cost, install cost versus life cycle cost, production load schedule criteria, plant startup layoff criteria, energy daytime tariffs criteria with adopted production, footprint of mechanical dimensions. Those are basic criteria. And the bottom line of every approach, every customer is special for us. And the way we approach the project is to work with our customers. We don't just deliver the equipment. We counsel our customer will live with the project and be supported for the lifetime.
Okay, thank you, Medina. Our next question asks, are there any specific situations where an IGBT chopper rectifier would be more beneficial than a Thyristor rectifier?
This question will be answered by Mike Allen.
So in situations where the low DC voltage fluctuates regularly, chopper rectifiers are not subject to the AC line power factor fluctuations of the equivalent SCR rectifiers. Also, if your process requires a higher starting voltage, and a lower dwell voltage, such as plasma applications. You can size your system based on the power and potentially reduce the size of your overall system.
Okay, thank you, Mike. Our next question asks, given the higher efficiency and lower harmonics, is there less equipment required in comparison to a thyristor rectifier?
Thyristor rectifiers, as well as chopper rectifiers, diode rectifiers on their own, looking at the full output rating when the equipment operates at full output, harmonics pretty much look the same. But the major difference between the three topologies will be in chopper topology, leading with harmonic generations and power factor, keeping it constant throughout the range. With diode rectifiers as well as thyristor rectifiers, as soon as they go off their full rating, meaning full DC current and full DC voltage, the harmonic generation as well as power factor start changing. Lower the voltage, lower the power factor. So that's the basic and the biggest difference between the three topologies. Taking in account different pulse configurations for each of these systems, the harmonic content as well as power factor will change. Higher the pulse output of the systems, lower the harmonic content, and closer to IEEE 519 requirements. So if we would look at 18 pulses, 12 pulse, 18 pulse, 36 pulse, and so on, we've seen even systems installed here in the United States that are 48 pulse, the harmonic content will go down. So using any of these topologies, we can't avoid harmonic content generation. That is just the nature of the beast. So then looking at the size of equipment, Thyristor rectifiers will need compensation equipment, and that power factor and harmonic compensation equipment can be quite large. So for that token, there is way more equipment to install, and that will occupy the installation room in the facilities for Thyristor rectifiers than for chopper rectifiers.
Okay, thank you for that answer, Medina. Now, our next question asks, how old is the chopper technology?
The chopper technology is actually very old. With the age of the first drive that came out to the market, chopper technology was born. There were actually several manufacturers out of the market that have been producing high-power choppers. Now, chopper technology on its own is a part of any drive system, and drive systems are voltage sources. When it comes to high-power choppers are actually current sources, and that's the basic and the biggest difference between the two. With high-power choppers, what's important that besides the power, the current for the system that is required is generated. So going back to early 80s, 90s, first high-power choppers started coming out. SATCON, at the time Inver Power Technologies, produced quite a lot of and installed quite a lot of high-power choppers, and they're still operating in the market. And for the fact, though SATCON and Inver Power have been out of business, Dynapower has been visiting those installations, and we have been working with our customers on upgrading the equipment and supplying electronics that is actually produced by Dynapower, and the electronics that can continue the life of that system.
Okay, great, thank you. Our next question asks, do chopper modules reduce stress on units?
Chopper technology itself actually reduces the stress on units. Modules are just a modular approach to building the system, chopper system. due to the operation and the way thyristors are operated and being turned on and off because of their very slow response time. The stress on thyristors is much larger than it is on IGBTs. So when it comes to component stress, yes, chopper technology puts way less stress on the components than thyristor technology.
Okay, great. Thank you. Our next question is asking, are companies oversizing drives so they can provide VARs to improve system power factor as a side benefit?
Peter, would you like to answer?
Yeah, I'll answer it. Typically not. VAR compensation from drives is a very unusual feature, and the drive would have to be specially ordered so that it would be able to supply volt VAR support. Drives, depending on if they're 6-pulse or 12-pulse and whether they're 100 horsepower or 1,000 horsepower, of course, are built very differently. We typically do not manufacture drives, but we understand the technology. It's very unusual to provide VAR support. In a different product built on a similar platform, an inverter product, also done in high-frequency topology, we do supply VAR support, but not in this, not in the power supply world, and certainly we have not seen it in the drive support.
Okay, thank you for that answer, Peter. Our next question asks, are there situations where a Thyristor rectifier would be better suited, and does Dynapower make high-power Thyristor rectifiers?
The answer is absolutely yes and yes. Dynapower has been producing and manufacturing Thyristor rectifiers for a long time, ever since actually Dynapower was established. That was our core product. And there is a lot of situations where Thyristor rectifier is more suitable than chopper rectifier, especially in smaller equipment where chopper rectifier simply becomes too expensive for installation. Dynapower has been also, along with small Thyristor rectifiers, in business of high-power rectifiers for a very long time. And as Richard mentioned at the beginning of the presentation, Dynapower acquired Rapid Power that has also been, for a number of years, over 40 years in business with high-power choppers. And our high-power choppers are located throughout the world and actively functioning, and we are actually producing and building some of high-power Thyristor applications and systems right now in our factory.
Okay, great. Thank you for that answer, Medina. Our next question asks, can you tell me more about Dynapower's history in designing, building, and deploying high-power rectifiers, and in what applications?
We have built many large power supplies, and one example, good example that we have today is U.S. Steel in Dearborn, Michigan, with 74 28,000 amp power supplies that they have been running since 1984. And this kind of projects that we have been dealing with was one of the large ones that we did, and U.S. Steel has been benefiting for double-side galvanizing steel.
Dynapower has also been very active in mining industry, in the electrochemical industry, as well as metal finishing, smaller rectifiers. But we've been having large installations that were going over hundreds of rectifiers at the time. If you want me to speak about more about different applications like mining applications, those are very, very large installations that rate over 50,000 amps and much higher. We have also installations of Thyristor rectifiers as well as chopper rectifiers in that industry. We have been very active in electrochemical industry where we are supplying Thyristor rectifiers mainly, but also chopper rectifiers. Lately, we have been tackling the plasma applications, and we have been actively working with a company, Tetronics from UK, and some other companies that we have been supplying choppers to.
Okay, great. Another question is asking, what is the typical chopper drive frequency?
Our standard chopper runs at the IGBTs at 2 kilohertz, and those are each module has 4 IGBTs that are phase shifted, so you'll see 8 kilohertz at the output.
Okay, great. Our next question asks, can you explain the effect of the harmonics generation and power factor quality in different typologies?
This question will be answered by Mr. Peter Pollack.
So the two very separate issues. So let's take power factor first. As I think Medina mentioned in the presentation, SCR units are typically considered a current source and choppers are considered a power source. What that means in essence is that in order to regulate an SCR unit, you control the phase angle of the SCR. When you retard the phase angle of an SCR unit, you reduce the power factor. In a chopper unit, the diode bridge rectifier, followed by an IGBT switch, so it's DC, as Mike said, running at 2 kilohertz, phase shifted to 8 kilohertz. But diode bridge has a constant power factor. So that's the difference in the power factor. Regardless of the output voltage and current, power factor on a chopper unit is constant. The harmonic difference is really dependent on the transformer configuration to any rectifier or drive for that matter. 6 pulse, 12 pulse, 24 pulse, the harmonics generated by these different transformer configurations are the equivalent of the harmonic number on either side of the pulse and 1 over that number. So a 6 pulse rectifier has 5th and 7th harmonic and 1 over 5 or 20% 5th and 1 over 7 of the 7th harmonic. As you increase the pulses, you decrease the actual current harmonic. So a 24 pulse unit has 21st and 23rd harmonic, and they are very, very small. So the idea here is that a polyphase system is what is done to reduce harmonics. And typically the bigger kilowatts, more power, the more advantageous it is to improve and increase the transformer configuration. I said 21st, I meant 23rd, sorry.
Okay, great. Thanks, Peter. Another question is asking, does Dynapower also make inverters and UPSs? And if so, what is the maximum kVA and for what application?
Yes, we make, the other half of our business is in energy and energy storage. So we make modular systems, bidirectional inverter converters in standard product ranges from 250 kilowatts up to 2.2 megawatts that are then paralleled. We have installations that are up to 10 and 20 and even 40 megawatts. Our most recent deployment of inverters was 22 megawatt inverters for a 40 megawatt installation of energy storage on the transmission and distribution grid referred to as PJM. So yes, that's part and parcel of what we build for the energy storage industry, and now for energy storage coupled with solar as well. So the short answer is yes, we make that product. We make it for indoor, outdoor, liquid-cooled, air-cooled, and in fact, we built all of the 250 kilowatt inverters for the introduction of the energy storage for what we call C&I or commercial industrial deployment for the Tesla product several years ago.
Okay, great. Let's take a look at one last question, and it asks, why is the transformer design simpler for choppers than for SCR rectifiers?
It is simple. Chopper rectification and chopper rectifiers have actually two stages of rectification. The first stage, that's the stage that is towards the line, is a diode rectification, and right after that is IGBT, DC to DC rectification. Diode rectifiers require simple transformer. There is no need for tap changers and steps in bringing the voltage input. So it's the diode rectifier that determines the transformer design. Transformer design for chopper rectifiers is bridge, usually circuit 31 for 12 pulse or 6 pulse, or depends whether it's requested to be 24 pulse, and then we will do a combination of the transformers and vector offsets on the input. While Thyristor rectifiers, depending on the overall system topology, can go to a very complex design. The more impulses the design goes, the topology goes, more complicated the transformer is. Some of those transformers will contain the IPTs. Some will have higher kVA input. That all depends on the rectification and the circuit that is selected. So the losses of those transformers can go up. And also, if the DC voltage needs to be regulated, some of the transformers can include multiple of the tap changers. So the complexity of the transformer goes significantly high.
Okay, great. Thank you, Medina. And with that, we're going to wrap up our live Q&A right there. If we did not get to your question, someone will be following up with you soon with an answer. Thank you for attending our webinar today. Take care, everyone, and have a great rest of your day.
We want to thank all the participants, and we will be coming up and following with any other questions if they come after live webinar, as well as posting the existing webinar. We will follow up with some other topics, so please stay tuned, and thank you again for participation.